Good morning, here we are again. It's the physics video lecture, Physics 2A video lecture 19. And we're working on momentum and collisions. Decided to bring this demonstration back in and review what we've done so far. So we're doing momentum and collisions. I'll just list our definitions and our major results. We have the momentum being the mass times the velocity. We had the impulse being equal to force over times a certain amount of time. Typically we think of it as being a short time. Okay. And that turned out to be the change of the momentum. I'll just write delta mv. And then we had, if, a number of things right here, if the net external force on a two-body system is equal to 0, I'm going to write if F net equals 0. But what we want is that conservation law, M1 V1 plus M2 V2. So that's the sum of the two linear momenta before the collision is equal to M1 V1, and prime just means after, plus M2 V2 prime. Right? Your book will use initial and final. I'm just putting an unprimed and a primed. Saves us a little bit of writing. So that's the law of conservation of linear momentum. And we've already done a number of applications. And what I'm going to do is review the applications in the sense of just discussing these two cars colliding with each other. So they have Velcro on one side. Let's see if we can get them to stick together. There we go. So the inelastic collision is when they collide and stick together. Okay. And we see that they slow down quite a bit. We calculated that if they're equal masses, it's half the speed. We found the interesting and amazing result that kinetic energy is not conserved. It doesn't matter how gentle this collision is. If they collide and stick together, we even found equal masses lose half of the kinetic energy. So in fact, referring to these masses or these objects just by their mass doesn't tell the whole story. They actually have internal structure, and when we get to thermal physics, we'll be able to talk about that more. Okay. Because in reality, no energy is ever lost. It's not lost to the universe, okay? It changes form, and it changes form in more ways than one. Okay, so that was the inelastic collision. Let's just write down inelastic, and in fact, perfectly inelastic collision. This, by the way, is the one I always put on the exams. Okay, so this one you should just know very well. We get the perfectly inelastic collision, and you know that was when we, on the right side, it was equal to the sum of the masses times their common velocity. Okay, so we have another experiment that I drew your attention to, another demonstration. And that was, wait a minute, we want red, blue. There we go. That was with the magnetic repulsion, okay? So I can actually push these cars around and they never touch because they have magnets mounted in them. And I said those are internal forces, right? There's magnets mounted there. The external forces vanish because we have the normal force in the track. We have the weight of the car pointing down, okay? Now this collision here is going to reveal everything. So I've shown it to you before. One car comes in, comes to a dead stop, the other one goes out at the same speed. Okay. So that's key here, that the collision occurs with no actual contact. This one comes to a dead stop. We already know momentum is transferred, okay? That's conservation of momentum, but only with this symmetric one, with the equal masses, can we see that if we have the same speed after the collision as before, the energy is also conserved. So the demonstration here with what I'm going to call an elastic collision, and I'll even, I'll go ahead and sketch what we had here. We have M1, V1, we have M2, V2 equals 0, and M1 equals M2 in this particular demonstration. After the collision, we have M1, V1 prime equals 0, and now our M2 is moving. M2 V2 prime is equal to M1 V1. In fact, I'm going to make sure this is more clear. Since it was an equal masses demonstration, let's erase all of these subscripts for the masses. Okay. And then we can really specify this. So before we have MV1 and V2 is equal to 0, and after we have MV1 prime equals 0, I'll put a comma here, V1 prime is equal to 0, this is a stop, and MV2 prime is equal to MV1. So that's the idea of that. The collision where one comes to a dead stop, the other one moves out with the same speed, with the original speed. Because what we have here is that energy is being conserved. So momentum we already knew about, but here, energy is all right. Here, momentum and energy. Momentum and energy. And continuing this sentence on this board right here, here, momentum and energy are both conserved. You see why we had to start with the inelastic collision to get behind the, to figure out the idea that the energy is important. And here in the elastic collision, it's conserved, okay? Because momentum and the speed are the same, final speeds. Momentum and energy are conserved. Now, that's not always the case. So you could say this is a hypothesis. Momentum and energy are both conserved. It's no longer visible if you have unequal masses. For that, we're going to have to do a major calculation. Because if I come in against the large mass, this one moved back a bit and this one moved forward. Let's try it this way. Okay, so here's momentum. All right, this one, we saw this the other day, right? This one fires out faster, but this one keeps moving. Well, we no longer have this simple symmetry where we can declare that both energy and momentum are conserved. So that's actually, the energy aspect of this is still a bit of a hypothesis, but we're now going to do a calculation for the inelastic collision and see if the assumptions of energy and momentum conservation deliver results that explain these phenomena. That's the plan. So let's just call this elastic collision. And it's going to be two bodies. It's going to be exactly what I've drawn up here and demonstrated here with different masses. So we're going to set up two equations. The momentum equation, oh actually let's write elastic collision in one dimension. Okay, elastic collision in one dimension. So here's our momentum equation. We have m1v1 plus m2v2. You know, I left the vectors off, although these can still have positive and negative values, right? m1v1, m2v2 equals m1v1 prime plus m2v2 prime. So that we already know about. Now, if energy is conserved, and I'll just remind you, we're looking at 1/2 mv squared as our kinetic energy on the horizontal. I'm going to get rid of the 1/2s immediately, okay? So if I write down the energy equation, I have m1 v1 squared plus m2 v2 squared equals m1 v1 prime squared plus m2 v2 prime squared. Okay, I just left off the 1/2s from all of these. Now, two equations, two unknowns. So we imagine we're given v1 and v2, find v1 prime and v2 prime. So given v1 and v2, solve for v1 prime and v2 prime. That could get pretty tricky, but there is a little trick that's going to make it easier. What we're going to do is rewrite these equations in a certain way. So equation 1, I'm going to write as m1 times v1 minus v1 prime, and that's going to be equal to m2 v2 prime minus v2. Okay. So I brought the v1 prime over the left side, the v2 over the right side with its minus sign. In equation 2, I'm going to do something similar. So for equation 2, I'm going to get m1 v1 squared minus v1 prime squared. Okay. But I'm going to factor that as follows right away. Let's put this down here. v1 prime squared minus v2 prime squared is equal to v1 minus v2. Okay. Hold on. Better I just write it down first and then explain it. So I've got v1 squared, v1 prime squared, and that's going to be v1 minus v1 prime, v1 plus v1 prime. Okay, the difference of squares factors that way. Over on the right side, I'm going to take the m2, then I'm going to have v2 prime squared minus v2 squared, so it's v2 prime minus v2, v2 prime plus v2. Okay. So that is, and here now I'll write down what I did. I had m1 v1 squared minus v1 prime squared equals m1 v1 minus v1 prime v1 plus v1 prime. That's that difference of squares. Actually, before I go on, I think I got a mistake here. Yeah, so v1, gotta get that right. v1 plus v1 prime, v1 minus v1 prime. That's what does it. v1 prime minus v1 prime squared. No, I think we got that. Okay, one take, no edit, so make sure you get the algebra right. I think we have the algebra right. 2 prime squared. B2 squared. Good, we've got that. It'll come out on the wash if we don't. So now we have replaced these two original equations by these two, and there's a basic substitution that can now be made. And that is, we're going to find something identical here. Okay, so what do we have here? We have a V1 minus V prime, V1 prime, and we have a V1 minus V1 prime here as well. So we can substitute that into there. So we're going to substitute the first equation into the second equation, and we get M1 V1 minus V1 prime equals M2 V2 prime minus V2. Okay, so that is this right here, M1 V1, M2 V2 prime minus V2. But we're substituting it right there, so now we have V1 plus V1 prime equals M2 V2 prime minus V2, V2 prime plus V2. And what's great here is we get this cancellation. What's M2? These are the same. We'll do it red. These are the same. And so we're left with V1 plus V1 prime is equal to V2 prime plus V2. So that's just a statement about the relative velocities now. I can write or V1 minus V2, so the original difference of velocities is equal to minus V1 prime minus V2 prime. So if you write it in this way, it's a statement that the velocity, relative velocities are exchanged with a minus sign in front of them. More important for our goal here is that now we've gotten rid of solving any quadratic formulas, which would have been a nightmare. Okay. So this result in either form, V1 minus V2 minus V, yeah, this is right, a minus sign, difference velocity. This result in either form now gets plugged back into our original equation 1. So take this result. So next, take this result into the original equation 1 up there on the board and see what happens. So what we're going to be able to do is substitute one of these. So let's get rid of V1 in the first equation. Okay. So we have M1 times, and what is V1 equal to here? We could say V1 is equal to this, these two, subtract that one over. So V1 is equal to V2 plus V2 prime minus V1 prime. Actually, change my mind. Let's get rid of V1 prime in the first equation. Okay, we're going to get rid of V1 prime because we actually want to keep the originals in there. Okay, what's more with feeling? We're going to get rid of the V1 prime, so we're going to have M1 V1 plus M2 V2 equals M1, and now we find out what V1 prime is equal to. It's equal to V2 prime plus V2 minus V1. Okay, so that's M1 V1 prime plus M2 V2 prime. And now we'll just be able to solve for V2 prime. Solve for V2 prime. So what do we get there? We have, we'll do the V2 prime on this side. We're going to have V2 prime times M1, that's right there, plus M2, that's right there. Okay, strike these, V2 prime, M1, got that, that. And then we're going to have M1 V1 plus M2 V2. But what we'll do here is write the V1, we've got an M1, and we're going to have another M1, because this one with a minus sign goes to the other side. There's another M1, so we have two M1. And what else do we have? Plus V2, and we'll have an M2 here. And from this side, we have M1. Going to come over to the other side of the minus sign, so minus M1. Okay, good. So now I'm going to take this result and rewrite everything. Where are we? Okay. So now we're going to make sense of everything. I don't have to save any of these now. So what we did there was some algebraic tricks. Now we're about to write down the actual physical formula. So what we have is V2 prime is equal to 2M1 V1 over M1 plus M2 plus M2 minus M1, M1 plus M2 times V2. Okay. So here's our goal. We have the final result in terms of these two initial velocities, V1 and V2. Now, we can do the whole algebraic rigmarole again, but in fact, we can get the result by just switching ones and twos in here carefully. Okay. So if we switch all the ones and twos, we will have M1 minus M2 over M1 plus M2 times V1 plus 2M2 over M1 plus M2 times V2. Okay. So this calculation knew nothing about 1 and 2, right? Therefore, we could just switch those once we found one of them. And okay, so this is a major result of sorts. We had this idea and we applied it, and now we have these predictions for what will happen. So if you give me V1 and V2 and these masses, I'm supposed to get this V2 prime and V1 prime out again. And we have a test of this because we have the M1 equals M2 system. And if these didn't work out, I'd have to go back to the drawing board. So wish me luck. Okay, so example. We have M1 equals M2, V1 equals V1, okay, check that off, V2 equals 0. This is our favorite example, equal masses, right? Dead stop, keeps running. So what do we get for this example? We get V2 prime equals, and we go back to this formula. Remember, the masses are equal, so 2m over m plus m, which is also 2m. So we just get a 1 here times V1. V2 prime equals V1. For V1 prime, oh, by the way, V2 was 0, right? And M1 was equal to M2. For the V1 prime, we have M1 minus M2, but they're equal, so that's a 0. And then we have 2M2, V2 was also a 0, so we get V1 prime equals 0. Check. Okay. So that giant calculation gave us these formulas, and we assumed that energy is conserved. And we already had momentum was conserved, so energy and momentum conservation gave us this. So for that reason, this is a pretty major result. Okay, we did the work, we did the algebra, and we now have these formulas. There's another interesting example that actually has to hold true, and that is we're going to let M1 be much greater than M2 and V2 be equal to 0 again. And that is this one that I like to show you when we put some extra mass on here and send this in slowly, and this one leaps away with greater speed. Okay, that's the one we're looking for. So, these examples are both as important. So now if M1 is much greater than M2, we're going to get for our V2 prime. Now, M1 is much greater than M2, so say M1 is 10 and M2 is 1, then we can neglect the M2 in the denominator. So we're getting approximately 2V1. Okay, that's really important. Because if M1 is much greater than M2, the denominator is doing very little. Okay, so 2V1. And that's a 0 anyway. V1 prime, on the other hand, M1 minus M2. Again, the M2 is negligible compared to the M1, or if it's much smaller, then you end up with, and negligible down here, the V1 is relatively unchanged. So we're going to say approximately V1 prime, approximately V1. And again, these are both 0. So this is what you see. And of course, this car is not 10 times as big, but you're already seeing the effect. Comes in slow, that one gets launched fast. In the limit of this car, say, being 10 times as massive, this thing would shoot out at twice the speed, okay? So, and that, by the way, is the basketball and the tennis ball demonstration explanation. Okay, so that's a major calculation. It's worth it. You know, I'll assign one of these on the homework. In fact, I'm going to talk about the homework right now. Let's see how much time we've used. Oh, we've got nothing but time. But yeah, let's talk about a couple homework problems. So you're allowed to use these. I don't think our book actually solves them for you, but I just did. I think I'll just wrap things up. Well, now we got enough stuff to do. So the homework problem that I'm referring to would be, which one was that? changed my mind. Hold on. Okay, this is chapter 6, number 66. Homework problem 6, problem 66. Yeah. So this is a combined problem. You're going to have an elastic collision, and the idea is you've got a bead here and a bead down at the bottom, and you're definitely going to want to just solve this with letters before you do anything. They give us masses. I'm just going to say M1 and M2. Okay. So the thing is this is going to be an elastic collision right when it comes down. It's going to be a one-dimensional elastic collision. And this height here just allows you to calculate V1, because we now know, because of H here, we're going to have V1 will be root 2GH, right? We're used to that. Hope we're used to that. So then M1 comes down and strikes this other bead elastically. And so during that impact and immediately before and afterwards, you're on the horizontal. Okay. So then the question is, how high does M2 go up the wire, whatever this is, up the track? How high does it go? And that, of course, depends upon, so here we'll put H prime equals question mark. So how high does this thing go? And that depends on its speed. Okay. But you can just as well say V2 prime, that's its speed afterwards, is equal to root 2GH prime. Okay. Those are the energy conservation and even free fall formulas, so you're getting used to these. And so you can see what happened here. They translated this problem, or they just added this track business to talk about the final and initial velocities. So, but you have to go through the heights. So H prime is whatever, well, it depends on V2 prime and vice versa. Good. So that's a elastic collision of this type, and that's a nice problem. Okay, what else do we have to talk about? How much more time do we have? You know, I think I'll just wrap this up with a brief discussion of two-dimensional elastic collisions. So yeah, I need the full board for this, so I'll send this one up there. So just to remind us, we're doing all these collisions. We have inelastic in 1 and 2 dimensions. I'm going to give you another homework problem for two-dimensional inelastic collisions to wrap things up. Then we have these elastic collisions. Elastic collisions, okay. Now we did one dimension right there, and we got those beautiful results, okay. So one dimension, check off. And by the way, momentum is conserved, but energy is not conserved. Momentum and energy are conserved, right? That's what characterizes those both. So we have the one-dimensional. Now the two-dimensional is where it gets interesting, even more interesting. It's always interesting. And everyone has experience with this if you've ever played billiards, okay? You shoot a ball and you shoot one against the other, hit a bit on the side, and they scatter in different directions. So that's what I'm going to be talking about. Two-dimensional elastic collisions. We're going to have M1 moving along here, so we have M1 times V1, and we're just going to hit a target is at rest. So V2 is equal 0, target at rest. Okay, that's how we play billiards. So let's go ahead and put this on an x-axis. Okay, there's our x-axis, and we can have a y-axis here. Okay, so the balls collide, and then I've got colors, so I'll go ahead and I'll let M1 go out in this direction here. So that's 1. We have M1 V1 prime, and then 2 going to go down here. So here's 2 after the collision, and we have M2 V2 prime. Well, you'll see what's going on. There are some angles characterizing this, so let's go ahead and call this one theta and this one phi. And now we can set up our momentum and conservation equations. You'll notice momentum has 2 components. Okay, energy always only has 1 component. So let's write momentum equations right here. Momentum. We've got an x equation and a, you know what, I'm going to send this up. Use more board. So we've got a picture up on the board here. This one I can even leave up momentarily. So let's look at momentum and energy off of that picture there. So the x component of momentum, before the collision, we just have M1 times V1, that's it, okay? After the collision, we have the number 1 particle there, M1 V1 prime, cosine of theta, because the component of that vector in the x direction, cosine, we have plus M2 V2 prime, cosine of phi. Now momentum in the y direction, what is that? Originally we had none, so we have a 0 here. So we had no y component, we have 0, and then we have M1 V1 prime sine theta for our particle number 1, and particle number 2, because it's pointing down, I'm going to put the minus sign in by hand, minus M2 V2 prime sine of phi. And the energy equation we still have as before. So before the collision we have 1/2 M1 V1 squared. After the collision, M1 V1 prime squared, 1/2 M2 V2 prime squared. So you'll see there are 3 possible equations. Interestingly though, right, there are 3 actual equations. There are 4 possible unknowns, namely theta, phi, V1 prime, and V2 prime. So a problem like this can only be solved if you have some added information besides just coming in here with a certain momentum. But I will just write here 3 equations, 3 unknowns. And I'm going to assign one of these problems as well. There's a problem in the book where, you know, there's enough information given so you can solve for your unknowns. So yeah, it starts getting complicated. That's why I say you have to go play some billiards and get a feel for this. Billiards is actually more complicated because you can put some spin on the balls and do other things as well. But you know, fundamentally, this is what you're doing. If you do a perfectly head-on collision, you know, you get to go forward. Otherwise, you hit it a little bit to the side. One goes in one direction, one goes in the other. Okay. So what remains for me to do, check our time here, is, yeah, that's good. Let's write down what the other homework problems are. So now we're talking homework number 19. And I have written down here chapter 6. Chapter 6. Okay. So the first two problems, 49 and 51. Make sure. 49 and 51 are basically the same problem both times, maybe some different unknowns. They're two-dimensional inelastic. Two-dimensional inelastic. And I'll remind you what I told you guys last time. It's in the other lecture. If you have collisions happening at right angles, here, let's not draw a 45 degree. So some collision is happening at a right angle, like that automobile collision I talked about. In the book is a football players and automobiles. You've got your two vector, you've got m1 v1 vector plus m2 v2 vector equals m1 plus m2 v prime vector. Okay. So there's our equation. Long story short, this equation translates into this triangle. It's a right triangle in both cases, m1 v1, m2 v2, m1 plus m2 v prime, and whatever angle you want to place, okay? So you translate this directly into a labeled triangle, which then you can use to solve the problem. So that's for both of these, 49 and 51. Then I just told you about problem 66, that's a nice one. And I had another one there. Oh yeah, fantastic. So 66 I told you about, 40 is the one with the two-dimensional thing. 49, 51, I'll write the other numbers right under here. Yeah, right on. So 40 and 60 and 66. So that's a good set. Okay, there you have it. Enjoy those. See you guys next time.